Alright, good evening all. You are welcome to the tutorials with Eternity the Schoolboy. Today we'll take a look at chemistry. We'll continue from where we stopped in our separation techniques. We'll treat the last separation technique, the last and the most elaborate of them all, chromatography. So that's where we'll go into now. We'll take it off from there. So now let's look at chromatography. So whenever you hear the word chromatography, what comes to your mind? Actually, chromatography is used to separate what? Solutes from where? A solution. Solutes from where? A solution. Solutes from a what? Solution. Not one. Solutes from where? A solution. Now, basically, the basic thing you look out for when you are describing chromatography is that every chromatographic procedure has two phases. There's a phase we call stationary phase and a phase we call what? Moving or mobile phase. Stationary phase there's one we call moving or what? Mobile what? Phase. So there's always a stationary phase, there's always a mobile phase. Then you talk about what you want to the solution whose solute you want to do what? Separate. And we have at your level you want to focus on paper chromatography. Then I'll just say one or two things about gas chromatography. But basically we have column chromatography, we have paper chromatography, gas chromatography. We also have column what? Chromatography, basically. But I want to focus just on what? Paper at this level. I don't want to start going into column. Paper, then talk about gas, just a bit, but the main thing. But they have the same principles. It's just that what differ is what is the moving phase here and what is the stationary what phase here. That's what does what differ from each of them. Now, but whether they employ the same principle, it's the same principle of separating solutes from a solution based on how they adhere to the stationary phase and how they dissolve in the what? Mobile phase. So you just add a mixture of adhering in the stationary phase and dissolving in the what? In the mobile phase. The solutes that adhere to the stationary phase tends to move slower than the one that don't adhere to the what? Stationary phase. And those that dissolve more in the mobile phase tends to move faster than the one that don't dissolve in the what? Mobile phase. So it's just a mixture of dissolving, adhering, dissolving, and they dissolve and adhere, they keep separating based on the speed. And after the whole thing, after separating, they will just be retained. You see them retained on the stationary phase. You cannot get the stationary phase and trace the point of origin where you drop the solute and trace the distance each of the solutes travel on the what? Stationary phase. And measure it with the one, take it with the one we have in the standard, because each solute has its own distance it can travel on the what? Stationary phase of the chromatographic what? Stationary phase. Each solute substance has its own recorded standard distance it can do what? Travel. That's how they calculate it. It's beyond their level, but just know that this is what happens. So after that, now they will now compare it with the one in the standard. The standard is okay. this has this now, okay, that means this solute is likely to be what? This substance. Are we together? Now basically with this general overview, let's look at paper chromatography. I said that solute that adhere in the stationary phase, they move slower than those that don't adhere to the what? Much to the what? Stationary phase. Now, with this general overview, let's look at those that dissolve in mobile phase. They move faster. You know that mobile phase is one in that moves. Okay, they move faster. Now let us now, with this overview now, let us now describe paper chromatography. Paper what? Chromatography. Now, in paper chromatography, the stationary phase is the what? A strip of chromatographic or filter paper. The stationary phase is what? A strip of what? A strip of what? Chromatographic paper or filter what? Paper. That's the what? The stationary phase in what? Paper chromatography. Then actually what happens is why the mobile phase is a solvent. What happens is this: in a chromatographic jar, something that looks like this, something that looks like this, in a jar, something that looks like this. Let's assume this is the word chromatographic paper. Please look up. China, look up before you start asking me questions. Look up so you can understand before you write. This is a jar that contains the mobile phase, which is a solvent. Okay. Now this is a chromatographic paper or filter paper. Now this solution you want to separate its components. You can drop it somewhere here. Just a drop of it is here. Something like ink, something like chlorophyll, all those things. Now a drop is placed here, somewhere here, not here, somewhere here. Now this is the jar. You now get this strip of paper that you have dropped the what? Solution you want to separate its component, its solute. Now you put it inside this. Don't let the solvent to touch this. The solvent should be somewhere here. Okay? If you put it, as you put it, what will start happening is this: this solvent will start ascending. It will start doing what? Ascending, soaking this in the paper. You see it ascending. When you get to this place, it will start dragging this what? This solution you dropped here. As it's dragging it, the component of that solution, this paper has pores that can retain, adhere the what? Solute. All together. So but it's not visible with common eye. Now as this solvent is going up, it will drag this solution you drop here. And as it's going up, different components of the solution, there's one that may be soluble with the what? Solvent. Those that are soluble in the solvent will do what? Dissolve in the solvent, and they will drag up to a particular place up. They may be adhere to the what? To the paper. So what you keep seeing is adhering to the paper and dissolving in the solvent. As solvent is going up. Adhere, dissolve. Those that have strong adherence to the paper will be trapped in the paper. They will be moving slowly. True of us? True of us? Just like as you are here, we are 5 people here. Just as we are, let's assume we are 10 people here together holding this board. So we are like solutes in the what you drop here. True of us? Then a flood of water will come like this and start carrying everything here. Because my strength is I have more strength than what? Michael. And Michael, I don't know who Michael will have more strength than. At the end, because the strength of our grabbing this thing is not the same thing, right? Now, me that has higher strength to grab this thing, the flood may not carry me like that, two of us. But the person that's somewhere like Chinaya, for the flood will just sweep him. She see herself here. Two of us. I'm still there, but we are together here, two of us. So the flood is like this solvent going up. Someone like Michael, the flood will drag him. He hold my shirt and tear my shirt and come here. Someone like our fragile sister, the flood will carry her, throw her to that end of the wall. But the point I'm making is that we are together, but we are separated. Two of us. Chinaya is here. Michael is here. I'm there. Favor. I don't know where they will throw Favor. But the point is that we are now separated. As the flood that came from this side separated us the same way, this solvent going up will separate the component of this what? Some, at the end of the whole thing, you will see patches like this. Different what components will be on the paper like this. When this thing get up to 3/4 of this paper, you stop and bring it out. You see, if you dry it, you will see spots of different components. Now, this is what they now dry. If you want to, they can use color to distinguish them or whatever. But the point is that when they now bring it out, they can see different spots and measure the distance from the point of what? Origin. Each solute has a peculiar distance it can do what? Travel. It's already done, calculated, and kept as standard. So when you now measure a particular distance, you now go to the standard and say, okay, see the solute, the substance that has the same word distance. Okay, this is likely what? This what? Compound or this substance. Are we together? This is basically what happens in what? This paper what? Chromatography. So with that, you can actually know, separate and identify the components of the what? This what? Solution. Does it make sense? Does it make sense? So any other one we are talking about employ this principle, but what may differ is what? What they use as what? What they use as what? Stationary phase, and what they use as what? Mobile phase, and what you want to do what? Separate. But this I just described now is the basic thing in what? Chromatography. Okay? So now in gas chromatography, but one thing is that gas chromatography is more sensitive technique than what? Know that point, than paper what? Chromatography. That's one thing you should know. Gas is more extremely sensitive what? Technique. Very important. Now, but in gas chromatography, the stationary phase is just a liquid. In gas chromatography, the stationary phase is a liquid mixed with a what? Solid. And is packed in what? Is packed in long glass what? Column with small diameter. That forms a what? Stationary what? Phase. Liquid mixed with solid and packed in a long glass column that has what? Small diameter. While the moving face or the mobile face of gas chromatography is just inert gas, like fairly inert gas like nitrogen or helium. The name they call it is carrier gas. Please note that point too. I think I've seen this type of thing in past question. Carrier what? Gas. I say that the moving face of the gas chromatography is fairly inert gas. Fairly inert. Fairly what? Non-reactive gas. Example, you can use nitrogen or what? Helium. And this gas is named what? Carrier gas. Carrier what? Gas. So you can use gas chromatography to separate solids, liquid. You can use gas chromatography to separate both solid, liquid, and gaseous substances. Okay, you can use it for what? Both solids, liquid, and what? Gaseous what? Substances. Okay. So anything, just long story. So you just mix everything, mix what you want to separate with the what? Carrier gas, and heat it properly until it vaporizes. And you now pour it inside the what? Stationary phase, and watch it separate. Simple. But it's the same principle. Okay? Now, this is basically at this level what you need to know about what? Chromatography. When you come up and decide to venture into chemistry more, you start knowing, you learn more about these things. Let's stop here for now, please. I just want to have a summary of applications of what? Chromatography. Then we'll stop here. We'll stop there. Now, we have the question. Okay, ask.
Like you said that stationary phase and mobile phase, some phase, like now, some phase mobile phase and that of observing in stationary phase. Is there anyone that is particularly or specifically made for mobile phase and that of stationary phase, or is it that anyone can go?
Anyone can go. How? Let me understand what you're saying.
I said that he talked about the stationary phase now.
Okay.
And mobile phase. So that in mobile phase, dissolving takes place and it's more faster than that of stationary phase, and that of stationary phase is adhering to. So I'm not asking now, in separation now of substance, is there anyone that is specifically made for mobile phase and stationary phase?
No, see what happens. This is a mixture of different substances. As the stationary phase is moving over dragging the spot, what you dropped, the mixture over this, as moving over the stationary phase, is dragging them. Is dragging the what? Component. Some component may not be soluble.
Okay.
In the solvents. True of us. And if it's not soluble, can he actually drag it?
No.
Like that? And to even couple it with itself, some may even have more very, very high adherence to the what? Stationary phase. They will move slowly. They may move, but they move very, very what? Slowly, sluggishly. That at the end, they may just move a small distance. But the one that are soluble will just drive, boom, move fast. Especially those that don't adhere, move fast and move to the top. They are just the one that these things we don't know the components. We just use solvent. We don't know the component physically. It's when we see how they adhere. When we see their position in a particular on the paper after the experiment, you now go and read and know which one is which by the standard distance written on the words in the standard book. Okay, that is basically what happens. Because you don't know what the component is. We don't know. It's only when you now read the distance you can now say, okay. If let's assume that distance of, let's assume solute A is 2 cm or 10 cm. Let's assume. I'm just assuming. And you know the one you measured is around that 10 cm or 9.9. You can say, okay, that means this is this what substance. You can now carry out. That's where you now carry out other tests, true or false, to confirm whether it is what that substance. You may carry out other tests for that substance before you now conclude that this is the what? A substance. Okay? Good. So let's look at what are the applications of what? Chromatography. Let's go. In the hospital, it's used to do what? Determine the presence of certain substances in the blood and urine. In the hospital, it's used to determine the presence of what? Certain substances in the what? Blood and what? Urine of patients. This helps the doctors to do what? Proper what? Diagnosis. This helps the doctors to do what? Proper what? Diagnosis. So when you now, they tell you bring your urine, bring your blood, they'll take your blood. These are one of the, in a good hospital, standard hospital, those that have equipment. These are things they may carry out this to find out what are component of the what? Of the blood. To find out maybe there's something they don't want to know what and what are present in the blood that will help them to make a diagnosis of what that patient is what? Suffering. Even autopsy. In some autopsies, they may take blood blood of a living person to do sampling to know exactly what and what. Maybe somebody is suspected to have been injected with a poison, right? Or maybe the person that took a poison or something like that. They want to exactly know what is the chemical substance that entered the person's body. They can take blood, they can even take urine, carry out this test to identify different chemical substances in there. They will trace it and be able to say, okay, this is this substance. Okay. Is it clear? So this is also one of the applications of this chromatography. Now, it's also applied in petroleum industries. In petroleum industries, we talked about fractional distillation, right? Now, after fractional distillation, we get different fractions up here. There's also a possibility that this fraction may have other components that are small components that are not even entirely pure. So what happens is that it's used to identify various constituents of fractions obtained from what? Distillation of what? Crude oil. It's used to do what? Identify various constituents of what? Fractions obtained from what? Distillation of what? Crude oil. It's used of what? Identification. Maybe after separation, you can use it to identify the what? These constituents you got from where? This distillation. Now, of course, from what I said about if you check the distance, the substance can travel. You can go to the one that you have in standard and be able to identify that particular what? Substance. True or false? So in that case now, in research, you can say that in research, it can be used to do what? Analyze and identify substances. True or false? True or false? Because you don't know what is here. You only measure the distance it travel and check it with what you have in record and be able to say that this is X because you move the same distance with what? X. True or false? So you can, that's why I say that in research, it can be used to do what? Analyze and identify what? Substances. Now, in various health departments, if you go to the West, they don't joke with their health department. Here, I don't know. But I swear, God will help us. If you go to various health departments in civilized world, you don't just, they test these food substances they market and sell. Am I competing? to know exactly what are in a component, what level of preservative are in this what. There's level of preservative that you should not exceed. So this chromatography helps also to determine whether a particular food product has the required level of what? Preservative. Because preservative on their own are also what? Issues. True of us. We are trying to preserve food, but they are also what? Doing the other negative listing in the system. So there's level you should not do what? Exceed. So chromatography can be used to do what? To check if food products contain the required food preservative. That is preservative at a level that is not more than the what required. Okay, good. Now, apart from that, you can also use to check the constituent of what chemical products. True of us, since you can get a solution, because most chemical products are solution. True of us, some are solution. True of us, and since you can drop it and be able to separate it and identify, see, one thing with this nice, this doesn't just separate. It separates and does what? Help to do what? Identify. True of us. So because of that, now you can use chromatography to do what? Identify constituent of a what? Chemical substance. True of us. True of us. Good. You can do that. So far, that is a mixture. You can use it to identify the what? Constituent of what? The substance. You can use it to do what? Identify the constituent of the what? The substance. With this, I think we've come to an end of separation what? Techniques, okay? We've done test of purity, how to determine purity of substances, right? We talk about employing what? Melting and what? Boiling what? Point. True of us? True of us? Melting and what? Boiling what? Point. So let's not waste our time on this. So in our next class, we move to an entirely new topic. In our next class, we move to an entirely what? New topic. Let me tell you the topic we are going to go into in our next class. So we prepare ourselves towards that. In our next class, we go into atomic structure. Okay? We go into atomic structure and bonding. Atomic structure and what? Bonding. We go into atomic structure and what? Bonding. That's where we go next. Atomic structure and what? Bonding in our next class. Please I'm impressed with our level of review. At least we are waking up now. I want our chemistry review to be like this biology review. So that we make it what? Lively. We rub minds, okay? We rub minds and learn. All right. Any question? Any question? In the absence of question, we'll stop here for today. And I want to say a very big thank you for your attention and participation in today's class. It's encouraging. It's when you participate in my class, when you drag me in the class, that's when you bring out the best. That's when I will release all my arsenal trying to explain something. But if you come and become dull, quiet, if you dull me, to true of us. But if you bring up questions, try to find out reason why this should be this, then and trying to explain it, I will start pouring out everything. True of us. Trying to convince you, trying to explain it. That is what class should be. Not sitting down looking to some even run away because they not do the review. I don't know, Sha. I'll find out why some people I'm sensing that, but let me not confirm. But I'm sensing it. But let me not confirm. But see, I can't remember who the person I was talking to. I told the person, see, anybody that does not read and refuse to read will not like this review. Will not like this review because you will call to answer question. Three of us. This is how real life will throw questions and challenges to you to solve. As science students or scientists, you are problem what? Solvers. You are what? Problem what? Solvers. This is how life will throw real life challenges to you. So if you don't know how to solve problems, sorry, I don't know how you can cope. No matter any field where you want to go into, you must be a problem solver. For those that want to be pharmacists, you are a problem solver. True of us. So if you don't know how to solve problems, then I don't know what you are doing. I don't know what you are doing. So that's why I threw it like that. You only enjoy it if you actually do something. It's not true. It's not true. All right, so I think we'll stop here. God bless you. See you tomorrow. Sorry, Thursday.